So the differential equation is a function of x and y. And as you can see, this is a separable differential equation. And you know what we do when we have a separable differential equation? Yes, sir.
First you separate and then you integrate. Just follow these steps and you will do great. First you separate.
All right. Back to the problem.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.
Greetings, AP Calculus exam prep. Today we're looking at differential equation FRQs. And so we're going to look at the conventional type of problems. As we always say, when you actually do the problem, when you actually take the exam, it could have some novelties or nuances to it that we're not going to cover here. But again, your understanding of calculus and the prerequisite courses will help you maneuver through whatever nuances or novelties are embedded within the problem that you encounter. So let's get right to it.
Okay.
All right, so here's our first example, and we're going to look at 3 problems related to this example. You can see problem A is showing where they want us to draw a slope field. And typically on these problems, they'll ask us to draw a slope field or sometimes draw a solution curve. They'll ask us to find a tangent line equation and do a tangent line approximation. And then, of course, they'll ask us to solve the differential equation. And solving a differential equation is the biggest point getter of any free response problem that you'll do. So I'm referring to the letter problem. Of course, each numbered problem is a total of 9 points. But as far as lettered problems, the letter problem that deals with solving the differential equations is normally 5 to 6 points, which is generally the most points on any particular lettered problem. So anyway, let's look at this, look at our particular problem here, and let's work on solving it. So it says, consider the differential equation, dy by dx is y to the 4th over x minus 1. And problem A is on the axis provided, sketch a slope field for the given differential equations, for the given differential equation at the 6 points indicated. Now, normally how this type of problem is scored is normally 2 points, 1 point for the 0 slopes, and then another point for all the non-zero slopes. So what I like to do, I like to initially find all the 0 slopes and then find the remaining slopes. So if you look at the differential equation, again, I try to look for what's going to make the slope 0. And if you look, when y is 0, the slope is going to be 0. Irregardless of the value of x, with the one exception is when x is 1. But you're going to have to worry about when x is 1. You can see when x is 1 is blank because the function is the differential equation is not defined where x is 1. So, but when y is 0, the differential equation is going to be 0. So that means we can mark 0 slopes at the point where y is 0. So you see, I marked the 2 0 slopes at where y is 0. And from that, we now have 4 points remaining. So we have the point 2, 1, 2, 2, 0, 1, and 0, 2. And what we're going to do is just plug those values in for x and y in the differential equation. So for the point 2, 1, I'm going to plug in 2 for x and 1 for y. And whatever we get for that slope, we're going to make a little line element indicating that particular slope. So let's look at when x is 2 and y is 1, which is this point right here. So we plug in 1 for y, 1 to the 4th is just 1. We plug in 2 for x, 2 minus 1 is just 1. So that's 1 over 1. So the slope at 2, 1 is simply 1. And so we make a little line element there of 1. Of course, the slope of 1 is about 45 degrees. You just need to make your slope look close to what the actual slope is. There's no need to panic and bring out a ruler and try to make it exactly a slope of 1. It just should be fairly obvious of what the slope is. And next, let's look at the point 2, 2. So if I plug in 2 for y, that's 2 to the 4th, that's 16. And 2 for x again is 2 minus 1 is 1. So that's 16 over 1. So the slope is 16. So it should be, steeper than the slope of 1. So, something like that indicates a slope of 16. And now we have the 2 remaining points, 0, 1 and 0, 2. and the point 0, 1. So 0 for x, 1 for y. Again, 1 for y, y to the fourth is 1. And 0 minus 1 is -1. So you have 1 over -1. So the slope at 0, 1 is -1, something like that. And if we go to the point 0, comma 2, so 0 minus 1 is -1, and 2 to the fourth, again, is 16. So it's 16 over -1, or -16. So the slope should look something like that. And that's all you have to do for the slope field problem. Again, this is normally 2 points, 1 point for the zero slopes, and then another point for the non-zero slopes. All right, let's look at our next example, the next problem rather. So in the next problem, it says let y equal f of x be the particular solution to the given differential equation with initial condition f of 2 equals 1. Write an equation for the line tangent to the graph of y equals f of x at x equals 2. Use your equation to approximate f of 2.1. So here they want us to do a tangent line equation and a tangent line approximation. So make sure you do both to get your full amount of points. Sometimes, and I do this myself, sometimes we go straight to the tangent line approximation and forget in the process to first write the tangent line equation. So let's do a brief review of how we do a tangent line equation and a tangent line approximation. And all you have to remember is a tangent line equation is really based off point slope form, which you learned in Algebra 1. And so point slope form is there. So y equals m times x minus x1 plus y1. And, you know, it's, of course, a form that's used to find the equation of the line when you know the slope and you know some point x1 comma y1. Some people will have the y1 on the other side and have it y minus y1 equals. Of course, that's the same thing, just a different location for the y1. So for the tangent line equation, it's pretty much the same. You know, we use x naught and y naught for the initial condition, and it's still m times x minus x naught plus y naught. But the stipulation on this is that m is the value of the differential equation evaluated when x equals x naught and y equals y naught. And of course, the x naught, y naught represent the values of the initial condition, which is f of x naught equals y naught. So that's how we do the tangent line equation. And the tangent line approximation, if we think of the tangent line equation instead of just y equals as y of x, the tangent line approximation for y of a, we're just replacing x with a. So the tangent line approximation looks something like that. So let's go ahead and find the tangent line equation and tangent line approximation for the given problem. All right, so this is our given problem. So this is the differential equation for this particular problem. And this is our initial condition. So 2 is my x naught and 1 is my y naught. And they want me to find approximate the value of f of 2.1. So again, so the equation for the tangent line, so we want to find the equation of the tangent line first. And that equation is y equals m times x minus x naught plus y naught. Now, m is what we have to find. And m is the value of the differential equation where x equals x naught and y equals y naught. So this particular m is going to be dy by dx, where x equals 2 and y equals 1. So we're just going to plug in 2 for x and 1 for y. And that's a value we actually already found when we did the slope field. But we can look at it. If we plug in 1 for y, that's 1 to the fourth, that's 1. And we plug in 2 for x, that's 2 minus 1, that's 1. So that slope is 1. So we now have enough information to write the equation of the tangent line. So the equation of the tangent line will be y equals 1. I don't have to write the 1. The slope is 1 times x minus x naught is 2 plus y naught is 1. And so if you want, since the slope is 1, you know, we can write this as x minus 1 is the equation of the tangent line. Now we want to show the equation of the tangent line, and you know, I didn't need to simplify this, but it was just so simple since the slope was 1. If the slope was something other than 1, I would have left it in that particular form. And so now we do our tangent line approximation. So, and we're approximating for f of 2.1. And so f of 2.1 is approximately, and I'm just plugging in 2.1 in for x here. So 2.1 minus 1, or 1.1. So there's our tangent line approximation. So on a tangent line equation and approximation problem, find the tangent line equation first, and then to find the tangent line approximation, you're simply going to plug in the value you're approximating for in for x into the tangent line equation. Simple enough, correct? All right, let's look at our final problem we're going to do on this particular example. So the last problem, it says find a particular solution, y equals f of x to the given differential equation with initial condition f of 2 equals 1. So again, this is the big money getter. This is normally 5 or 6 points. A very important thing to do is to make sure you show the separation of variables. If you don't show the separation of variables, the maximum amount of points you can get, whether it's 5 or 6, is 0. So even though you can do it, maybe you can do a lot of this in your head and you can kind of just go right to the solution without showing anything, you have to show the separation of variables. So it's very important. So if you don't show the separation of variables, the maximum amount of points you can get on this big money getter is 0. So let's go ahead and work out this particular solution. All right, so we have dy by dx equals y to the 4th over x minus y. So the differential equation is a function of x and y. And as you can see, this is a separable differential equation. And you know what we do when we have a separable differential equation? Yes, sir.
First you separate and then you integrate. Just follow these steps and you will do great. First you separate.
All right. Back to the problem. All right, so let's go ahead and separate. So dy over y to the 4th is going to equal dx over x minus 1. First you separate. Let me move this term up here and make it y to the negative 4th. Dy equals dx over x minus 1. So first you separate, then you integrate. And so the integral of y to the negative 4th is going to be y to the negative 3 over negative 3. The integral of dx over x plus 1, dx over x minus 1 is going to be ln x minus 1 plus some constant. And what I would like to do, I'm going to write this y to the negative 3rd over negative 3. I'm going to write it as negative 1 over 3y cubed. So this guy right here, just going to move this negative guy up here, which is totally legal with a fraction. And I'm going to move this y to the negative 3 down here and make it positive y cubed at the bottom. And that's going to equal ln x minus 1 plus c. All right. So after I integrate and it's simplified fairly nicely, I like to find the value of c right after I integrate. Some people would put it in y equals form and then find c. I find it, more advantageous to find c, right after I integrate and the function is looking okay. So again, the initial condition was f of 2 equals 1. So we're going to plug in 1 for y and 2 for x. So if we plug in 1 for y, this will be negative 1 over 3. And if we plug in 2 for x, this will be ln 1 plus c. Ln 1 is 0, so c is going to equal negative 1/3. And so we have negative 1 over 3y cubed equals ln x minus 1 minus 1/3. So now we simply got to put this in y equals form. And so let's say I multiply everything by 3 first to get rid of this 3 here. So I'm going to multiply everything by 3. And when I do so, this 3 is going to cancel. So that's going to be -1 over y. Should I multiply by -3? -1 over, no, I'll just multiply by 3. All right, multiply everything by 3. This is -1 over y cubed. And that's going to equal 3 ln x minus 1 minus 1. All right, so when solving an equation like this, you can make these two guys switch positions. It's just a little algebra trick. It's not much of a trick. And if you understand why, we can just make those switch sides. So just imagine if I multiply both sides by y cubed, so that would disappear, and it would be this times y cubed. And then to get the y cubed by itself, I would divide by this. So what happens is they just switch places. So I'm going to make these switch places. I'm going to put the y cubed first, and I'll get y cubed is -1 over 3 ln x minus 1 minus 1. So again, I just switched the y cubed with this guy. And so you got y cubed equals -1 over this guy, but I put the y cubed first. And then, of course, our last step to solve this differential equation is simply to take the cube root. So y would be the cube root. Well, the cube root of -1 is -1, so you can keep the -1 like that. So -1 over the cube root of 3 ln x minus 1 minus 1. All right, so there you have it. So that's how you handle these differential equations. Differential equation FRQs. We looked at finding the slope field. We looked at doing the tangent line equation and the tangent line approximation, and we just looked at finding the particular solution. The only other more conventional thing that you normally see that we didn't look at was drawing a solution curve, which is fairly simplistic, but we didn't cover in this particular video. So I hope this helped you on your path to getting your 5 on your AP exam, and we'll see you next time.
First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing. Problem after problem until the day's end. Solving, keep solving, and turn the page in, and still keep grinding. Solutions keep finding. I have never seen a problem like this, but I know exactly where it fits. First order, separable, ODEs. Now I know what to do, holy me. First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Kind of a mathematical outlaw, a kind of a mathematical gangster.